Hello, thanks for joining us today. We're going to be doing some more image builds, so you're going to get to watch me fumble around with a terminal and my VS Code IDE. So today we're going to be explaining FIPS, or FIPS compliance, and we're going to show how we use some changes to the Go toolchain to be able to build Go applications that are FIPS compliant. You won't necessarily have all of the pieces to be able to recreate this because it relies on having access to a FIPS compliant OpenSSL implementation at the end. But all of the first couple steps and showing how we build everything works fine too. If you do have your own access to an OpenSSL 3 that is FIPS compliant, then you should be able to do this yourself. You can get that from us. You can get that from a bunch of other different vendors too. So let's jump in. I'll start screen sharing and we can get going. So the first FIPS package that I was hoping to start with today is actually the Cosign tool, which is part of uh, SigStore. So we're going to mess around and submit a PR with a FIPS compliant build of Cosign. Once you get this build, remember that you're still going to need to couple this with a version of OpenSSL in your final image. And that OpenSSL build will have to be FIPS compliant. But we'll get through these first couple steps ourselves. Let's start by taking a look at the build for Cosign itself here. This is our melange configuration file to build Cosign. Make this a little bit bigger, sneak that over. And as you can see, the very first thing we do is grab the source code from SigStore. And then we use our Go build pipeline, which kind of just runs Go build and passes a bunch of LD flags. One change we're going to have to make here is turning back on CGO. So this turns off CGO to prevent Cosign from using any native C code or libraries, but for FIPS, because we're going to use the normal build of OpenSSL, we're going to have to turn that back on. The main other difference is that instead of using normal Go, we're going to have to use our fork of Go, which has some patches to stop Go from using its native cryptography and fall back to OpenSSL libraries that are installed on the host at runtime. So those are the first changes that we're really going to have to make here. And I'll show you a couple different ways to show that it's working and all of that too as we get going. So let's start. I'll jump over to the Cosign repo and we'll take a look here. The very first thing I'm going to do is just start up a container with Wolfie inside of it that we can use to install stuff and try it out. So let's do that. All right. Instead of adding Go now, I'm going to add Go FIPS. That's the name of our Go FIPS package, which has the changes to Go to make it fall back to native cryptography instead of using its own inbuilt version. And we'll grab Git as well so we can clone the repo. The patches to Go FIPS are open source that we use. They're sitting there in the Wolfie repository. It's a bunch of small changes to the way that the cryptography implementations work. So if certain environment variables get set at runtime, then it changes the runtime behavior and links to C code. We can take a look at those in a minute once we get everything up and running just to show how it works. All right, awesome. So we have Go and Git. So let's do a Git clone of the SigStore repo. I'll do one of these as well to show it with the normal version of Go after in another container. All right, so we have Cosign and we have our Go FIPS tool. So this is Go 1.20, I believe. Yeah, awesome, 1.20.8 with our FIPS patches applied. So let's just do what are those flags here in Cosign? Yeah, so just stripping some stuff and then setting a package version. We can drop that for now. Let's do cgo enabled equals 1, go build cmd Cosign. We're going to download a bunch of Go modules from the Go module proxy that we have set up. Then it should compile. I'll grab a couple other utilities here too, just to show how we can tell that this actually worked and includes the changes to Go to make it dynamically load OpenSSL and then use the OpenSSL FIPS implementation at the end. Some of this is a little bit counterintuitive, but if you look at the patches to the Go compiler, then we can see how it all works and how it's all plugged together. So many Go modules. People always joke that Cosign pulls in the world, and it kind of does. It supports all the different KMS providers from different cloud providers, and they have huge dependency trees. So if you want to use GCP KMS or Azure KMS or Amazon KMS, the dependency trees get huge here. All right, so it's done downloading. It's probably compiling now, and it's a little bit slow since we have the CGO support turned on, and it's going to be compiling in a bunch of native C code. This should finish up in just a second. So what these patches do is make any cryptographic operations fall back to OpenSSL instead of using the Go version. Let me do, cool. All right, so we can do dn cosine, and we can see that now this is a dynamically linked executable. It's not static anymore. This is dynamically linked to libc and a couple other things. You could set this all up to compile statically, but that's much harder. Instead, we're going to rely on the host version of OpenSSL, which makes it easier to swap out to. But interestingly, you will not see OpenSSL in here. You might think that this is going to dynamically link into OpenSSL and you'll be able to see it here like libcrypto or libSSL. But it doesn't work that way. Instead, it does a DL open at runtime. And so we can see how that works by jumping here into the patches that get applied to Go. Here is our Go FIPS package here. And we have some patches in here that get applied after we clone the normal Go branch. Let's take a look at this overall build. So we get the normal build of Go. See here, it's just the tarball directly from the Go team. And then we apply a bunch of patches to it. So the patches are in that directory. After that, we basically just do the build and strip out some documentation and other things that we don't need at runtime. But a lot of these patches are changing it, changing the vendor tree so that it uses boring crypto instead of the typical crypto baked into Go. And then has support for dynamic linking and environment variables to configure this behavior. So you can configure the boring SSL fork here. There's some test changes. There's a crypto changes themselves to the algorithms. So EC, DSA in here. And instead of using a native Go version, it's actually using that C version with CGO support. We can see where it actually does that here. So if we search for DL open, here we go to a different patch. It supports a couple different versions of libcrypto. So there's 1.0, 1.1, and 3. And so it kind of goes through in this fallback pattern once we have crypto turned on here and runs a DL open on this. So that's why you're not seeing it there with LDD. But we should be able to verify this behavior a couple different ways in our compiled binary. The first one shows that the way that we actually do these tests when we build our final images. So the Go tool has a way to parse the Go binary and show different functions and things inside of it. And so since we built it this way, we can do Go tool nm, that's the name of it. I forget what it stands for, but it's going to print out a bunch of stuff from inside the binary if we pass it. So we have /cosine here that we just built. If we do Go tool nm and look for boring, nm cosine boring, we'll see all of these symbols in here. So this is the OpenSSL FIPS CGO support. We can see how this is embedded into the binary. And if we build it with a normal version of Go, which I can do in a couple minutes, we'll see that this isn't there. And in fact, it's statically linked and uses Go native cryptography. The other way to do this is to look at it with strace. So let's add strace and just see what actually gets opened up at runtime. And this will explain a little bit more of how it works too. So we can do, let's generate a key pair with cosine. When this starts up the binary, it should load this in every single thread. Let's do that just to hide some of the output. Actually, let's generate the key pair first because that requires some input, and then we'll do a sign blob or something like that. Type in a password. Cool. Now we have the key. Now let's do cosine, sign, blob. Redirect some output to hide it. Let's sign the README. We'll set the key to be cosine.key that we just created. And let's look for open calls. Oh, /cosine. There we go. Cool. So we can see here that we went through some of this fallback stuff. We loaded the dynamically linked cache, libresolve, libc. These are the things that showed up when I ran LDD. And then lib crypto got popped open, and there's a couple fallback paths here actually, because we tried lib first and then we tried user lib, which is where it actually was. So that finished. Now down here is where we see some of the rest of the way that this works. This is loading the OpenSSL configuration file. At runtime, OpenSSL can load this file, all the libraries, and that file can specify which algorithms are allowed, which mode to operate in. Because we have a standard one in here, this doesn't actually require FIPS mode. This is just a standard image with a standard OpenSSL.conf. It's going to work normally. That means that we can just drop this cosign into a different image, though, that does have the hardened FIPS configuration here. This gets loaded, this gets picked up, and then OpenSSL will operate in that mode, which should ban certain algorithms, ensure certain random number generators are used, and all of that other fun stuff. Let's take a look at what's in that file here. Oh, something screwed up my terminal. Let's try clearing it. Okay. What was that file name? Here we go. Etsy SSL. This is the basic configuration here for OpenSSL itself. Example configuration file. You can pass in other configs. They have a lot of different options in here. Yeah, but you can specify certain certificate extensions are allowed or banned. See, here's some FIPS stuff in here. If you get rid of this line here to include the FIPS module, then this adds a whole bunch of other requirements for OpenSSL, which specifies how to operate. So to turn on real FIPS mode, you need a real OpenSSL with the fips.so shared library, and then a FIPS configuration there too. More FIPSy stuff. So because we don't have that specified here, then cosign is going to continue to work normally, but this build should be able to drop in there and just work. Let's APK, let's get rid of that version of Go. Let's add normal Go. Hopefully this works. Cool. I'll back up that build of cosign, and then we can build a new one and see the differences. Okay. Let's do it. Let's keep cgo on for now. Don't actually know what the normal behavior is for cryptography with just cgo. I hope it still prefers the Go cryptography, but we'll see in a minute. Here we go. All right. Same shared library linkages in here. Now let's strace it again. Awesome. So no cryptography this time. Perfect. So it uses the inbuilt Go cryptography instead of OpenSSL on the host. You can see that the patch worked. Now let's do, keeps killing my cursor. And yeah, there's only a couple internal boring functions here instead of that full set from before because of those patches to Go that we applied. So this build of cosign, when combined with a FIPS compliant or validated OpenSSL library, should now be compliant for FIPS itself, FIPS 140-2. Let's exit here. We can then write up some YAML, test this out in a full melange pipeline, and then maybe even submit a PR. So let's close that terminal. I got a bunch of messy stuff in here. Let's start by copying cosign to FIPS diagonal. All right. We'll change that to Go FIPS. We'll change, oops, that's the normal cosign. Change this to cosign FIPS. Drop that to 0 because we don't have any yet. We'll do Go FIPS. We'll turn on cgo. And I think we have to change this part. Yeah, to Go FIPS/build. Cool. This all looks good. Let's give it a try. I have my massive terminal here. I was building Erlang yesterday. All right, let's let it run. No. Let's try. I think my paths are set up incorrectly. Here we go. There we go. All right, we got the build going. So it's going to download, install all those dependencies. This all works. We can lint it, check some updates, and then submit this package. And after this works, if we get this to build and get the PR sent up, I can show a little bit more about how the hardened OpenSSL FIPS package works too, which is in our private repository. But I'll pop open the IDE and show what those configurations look like and how we typically do those builds, even though it's not public. The way that we do FIPS in this strategy varies a little bit by language. If it's just C code, it's actually pretty easy. We just need to make sure that it compiles against our build of OpenSSL, and then we can swap out OpenSSL at runtime. So not too much actually has to change during the compilation process, and we try to compile against our build of OpenSSL and dynamically link that in anyway for most C programs, because that allows us to patch the cryptography pretty easily just by bumping OpenSSL. For Go, where it has its own cryptography built in, we also need to use a patched version of the Go compiler. We have some hybrid setups like the Nginx Go ingress controller, say for Kubernetes, which bundles both C code and Go code into a single package. So for there, we need to make sure that we do both. Build the C code, build the Go code with the patched Go, and then link them both against our FIPS compliant version of OpenSSL at the end. For Python, Ruby, Node.js, they all support dynamically linking against OpenSSL pretty easily anyway. So we have Python FIPS builds, Ruby FIPS builds. Node.js is a bit more complicated because Node typically vendors its own version of OpenSSL by default. So we do need to change the build of Node.js to use our version of OpenSSL instead of theirs. But we do that anyway, just to make sure that we have the ability to patch OpenSSL if there's a security vulnerability. We need to watch these things download again. But then we should be built in a second or so. I can pull up the Node.js configuration too to show how that works. See, so when we're building Node.js, we grab our OpenSSL. And then in here, we have to manually specify during the configuration step to use the shared library for OpenSSL that's already installed and use our default CA store and use the default configuration. If you don't specify these, then Node.js will actually go get its own build of OpenSSL instead of using ours, which means we can't do any of this FIPS magic. We do the same for Python. I think that's actually just the default when you do enable shared. So you don't actually have to do much muckery there because Python doesn't typically enable its own OpenSSL. But this is how if you just combine these Python and Node and Ruby builds, then you get FIPS and OpenSSL support. The hard part, though, is that OpenSSL in FIPS mode bans a lot of algorithms, like say MD5 and stuff like that, that are considered insecure. That's the entire point of FIPS, but if in one of these libraries or in one of these programs, if you try to call one of those deprecator banned algorithms, you'll get a crash at runtime. You can't really statically inspect all of the Python code to prevent that from happening. Applications might hardcode MD5 or something like that. Oh no, I broke something with source date epoch. I think I just forgot to pass something correct in here. I think there's a way to set that. Yeah, let me grab that. Try one more time, let that run, and then we'll set up the patch because I think that's automatically set as part of CI. All right, while this runs, we'll get that patch sent up and just run it in CI at the same time. Let's sign it with git sign. I should have done this first. We'll just format it. Oh, didn't change. We'll do an update check to make sure that that is set up correctly. Awesome. Now we'll push it and create the PR. What did I call a branch? Ah. It's hard zoomed in so far. Yep, it's under an OSI or FSF approved license. This is still maintained cosign. We've got the support policy, and we can drop the rest here. How's that build going? Still going, awesome. All right, let's jump over and take a look at how our private OpenSSL build actually works. It's in a different order because it's a private repo. Cool. Yeah, so here is the package that we have to drop into the image. We need to drop in OpenSSL config FIPS hardened. If you add that at runtime, and then also make sure that you grab the OpenSSL version as well. There's one other package. Let me find the name. That's our Ingress Nginx build. OpenSSL provider FIPS, this one. So this is what actually does the enable FIPS at OpenSSL build time. So this is the build of OpenSSL we use. This gives us FIPS, and it gives us the fips.so package and configuration file, which we make a couple tweaks to. OpenSSL is only really FIPS certified at version 3.0.8 right now, even though there's 3.1 and 3.1.1. They separately manage vulnerabilities inside of the separate FIPS module. And so if you need FIPS support, you need to stay on 3.0.8 for now, but we can still fix vulnerabilities on the outside surface. If there's a vulnerability found inside of the FIPS surface, then the module is somewhat invalidated until the change gets applied, and then the whole module gets revalidated. So unfortunately, you can end up in this situation where you have to choose between 0 CVEs and FIPS certification just because that process takes a while. The configuration file itself is here. This is where that gets applied. Let's pull up that openssl.conf and policy preamble section. This is a section we add to that to restrict the allowed cryptography algorithms and algorithm families to things that are FIPS certified. You'll see there's no ED25519. It's one of my pet peeves. It's widely regarded the best signature algorithm today, but it hasn't been FIPS certified, so it's not allowed here. And that's why cosign defaults to ECDSA. A couple other changes get applied in here, and then here's the rest of the FIPS section. This is kind of like that commented out section that was in the sample configuration that I showed before. So when you drop these configuration files in and you drop in that build of OpenSSL next to that build of cosign, then everything should be all hunky-dory and FIPSy. Did the build finish? Yes, awesome. We have cosign FIPS in there now. Let's see if it passed in CI. Yes. Oh no. What did we break? This looks like a flake in our build system. Let's take a look though. Yep, so the build actually worked and then it flaked cleaning up. So let's just do a quick retry. We still have to wait for the ARM build to finish. Once this is done though, yeah, we should be able to merge it and we get the tests all passing. FIPS, FIPS, FIPS. What other stuff could we FIPS? Let me explain this one a little bit too. So this is how Java works. There is a pluggable cryptography implementation in Java as well, just like in Go. Java contains a bunch of its own cryptography libraries and interfaces. But there's a project called Wildfly, which lets you swap out all of those cryptographic interfaces to ones that are backed by native OpenSSL. And then, similar magic and sleight of hand and layer of indirection, we can take that OpenSSL that this is then configured to use and swap in the FIPS certified version. So we have a couple different other little FIPS apps that we've done. We have, once Cosine makes it in, we have Cosine, and then we also have the Co-build tool. No one actually asked for this to be FIPS. I'm not really sure if it would matter to anyone, but we did that as just a little test run showing how the FIPS stuff can work together. Let's see if CI is, okay, yeah, it passed on ARM. Let's just kick this because it looks like it was just the cleanup that failed. Debugging flaky CI is always fun. Yeah, and then at that point, you can start to do the rest of the SIG-Store tooling too. We carefully designed everything like Recore and FullCO to only use algorithms by default that are allowed by FIPS. So swapping out the implementations is really all you need. If there were other things in there like MD5 or ED25519, the changes would have to be a lot more invasive. Let's see if it's going to rerun the entire thing. Yeah, probably. So this will take a few minutes to grab our runner. I'll let that run for a minute, make sure it looks good. And I can show what the, we can't actually build one of these images until this gets merged and built by CI and published. But I can show what the configuration in our images would look like in order to do that. Here is the repository with all of our image build definitions. And then we have a private version of this too, which has some of the FIPS stuff inside of it. It looks basically the exact same. Let's take, do we have a cosine image? We do, awesome. So this is how the cosine image is defined. There's some Terraform that we have set up here, specifying what to tag the images as, what to build them like, if there's different variants, all of that fun stuff. And then here is the actual YAML file explaining what we're going to install. We grab cosine. There's a bunch of shell redirection and stuff too, so we also give it BusyBox for any of the scripting. But this would instead change to say cosine FIPS, and then we would also drop in those two packages, the OpenSSL FIPS provider and then OpenSSL FIPS config hardened. And then once we have those two, it would just spit out and maintain, our automation would take care of that, all of these builds. If there's a CVE in OpenSSL, our automation would catch that and help us patch it and rebuild. If there's CVEs or new versions of cosine, then we would also automatically catch and rebuild those. Did this fail again? What's going on here? Maybe this isn't a flake. Yeah, this one looks weird. Let me make sure I've rebased everything. Otherwise I'll have to debug that flake later. Definitely doesn't look related to our change though, so maybe something else broke in the build tool chain. We'll let this run one more time. It's weird that it works on ARM, but that is what I tested it on. While this runs, another quick change we can make, unless someone made this already while we're here and everyone's watching, we could rename our OpenTF package. Oh, somebody already did this for us. I thought I was smart. OpenTF, the Terraform fork that's remaining under an open source license, came out a few weeks ago, but they renamed due to trademark issues over to OpenTofu. So that's the new name. We had an OpenTF package, but looks like somebody's already fixed this for us and renamed it to be OpenTofu. I like the name, although some people were complaining about it. But this should mean that we can do an APK add OpenTofu. And I think the binary is called tofu. Ooh, it looks like might have to change that one actually. I'll have to look up what the actual canonical binary name is. Why is Docker not running? Something's messed up there. Might have to kill Docker and restart it. The demo gods are not with us today. All right, our build is actually running. Let's see if we also renamed the image. Ah, there we go. We can fix that. Once Docker restarts, somebody renamed the package for us, but not the image. All right, we're all synced up. Let's go into here. Let's do cool. Do we have this repo opened up? Yeah, let's just do some swapperoos. How do we do find and replace? Cool. We have the technology. All right, if Docker is back up now, we can give this a try. All right, let's hop back over to here. We have to get our registry started to do our testing. What do I call that? Have it here. All right. So we have a local registry running. Let's do Terraform init. Get all synced up and ready. And then we should be able to build this OpenTofu image. And test it. We're using Terraform to build and test OpenTofu. Hey, it worked that time. Cool. Must have just been some flake that we were able to fix. All right, I'll click that and maybe somebody will merge it for us. Hey, and our test worked on that. Let's send a PR there too. What happened there? That was probably a mistake. All right. Set up this PR as well. This is a weird case. It's not a new one, so we can drop most of that stuff. because we published a whole bunch under OpenTF, we might want to actually delete those to prevent someone from actually accidentally relying on them. But at the same time, that would break people. So we might want to think through that a little bit. The rest should be good here. Awesome. We got 2 PRs sent up. Let's see if Docker is working now. Cool. Hey. Yeah, okay. So I think we might actually have to fix that. Let's look up OpenTofu. I thought I saw somewhere in one of the Hacker News comments that the binary is going to be called tofu instead of OpenTofu. If that's correct, we can go fix that. Let's see. Maybe it's here in this make file. Yeah, it is the tofu binary. Cool. All right, so let's fix that here, and then we can send another PR. It used to be called OpenTF, so I think we just assumed it would be called tofu. Bump that to 1. We recovered. We fixed the flaky CI. We fixed our Docker daemon. Stuff is looking up. Hopefully this CI passes, although at this one we'll also have to make a change once the new package goes in, because we'll probably have to change the tests. Yeah, so we'll have to change that. We'll have to change all these binary names and references. Package name will stay the same, but this will have to change. And okay, we don't have to change anything here because it just relies on the entry point. Awesome. All right, that built. Write a little commit message. We'll send a PR. We're on a roll. 3 PRs in 1 hour. And we'll just say you can merge in a couple different orders that would work. Awesome. All right, that was a pretty productive session. Hopefully we'll get some of these merged. Um, Great. So we built some FIPSy stuff. We fixed up some tofu, and we're good to go. Like this was a pretty good session overall. Thanks everybody. We'll end a little bit early, and reach out on LinkedIn or let us know if you have any other questions about our images or FIPS.